Welcome, everyone. For today's prep, I want to look at one more area calculation. So area for the region bounded between two curves. And for this example, we're going to look at a case where the two functions actually intersect. So we actually have these intersection points on either side. So sometimes this can happen. Rather than having a kind of a vertical line on the left, sometimes that maybe is where the two curves intersect. So it comes together at a point. And potentially, same thing on the right side. All right, so we have to first figure out these intersection points. Where do these actually occur? Now, we could probably figure out from the graph here that -1 is one of the intersection points. And then if I got out of the way, you could probably figure out that x equals 1 is one of the intersection points as well. But we want to confirm this algebraically. So our first step here, figure out the intersection points. Ooh. All right, so let's get our intersection points here. And how do we do this? Well, we take our two equations and we set them equal to each other. So we know that our two curves intersect. So if they intersect, that means both of these y values must be the same. So we can take the y value from the first function, which is the x squared plus 2x plus 3, and we could set the y value, take the y value from the second one, 2x plus 4, and we set them equal to each other. So let's do that. X squared plus 2x plus 3 is equal to 2x plus 4. So we set them equal, and then this gives us an equation to solve for x. And there's a few ways you can do this from here. So we can take all the terms from one side, and because this is a quadratic, we can move them to the other side. And normally with quadratic, you either try to factor it or you use the quadratic formula. So that's kind of like the default usually works types thing. Take all the terms, move them over to the other side, and then just get this equal to 0. We're going to Instead, for this one, we're going to do it a little different. We're just going to directly solve this one for x. So this actually simplifies down quite a nice so that we can just directly solve for x rather than having to try to factor it or use quadratic formula. So how are we going to do this? Well, both sides of this equation have a 2x. So we could subtract 2x from both sides and those cancel. And then we can subtract 3 from both sides. And when we do that, we get the equation x squared is equal to 1. So nice and easy. And then the only thing we got to do to get x all by itself is apply the square root. And whenever we apply the square root, it's not already there, but we apply it as we're solving for x, we just got to remember the plus or minus that goes in front. So x is equal to plus or minus the square root of 1. So we end up with x equals -1 and x equals +1. So yeah, the graph wasn't misleading. So we found that -1 and +1 were the two intersection points. All right, so we're going from one intersection point to the other. And we want to figure out, and we're going to start with -1. And then essentially we're just kind of getting this area for this region. So we're going to set up our integral. Now, before we do that, it's kind of clear because we have the graph here. But if you don't have the graph, or if you want to check it, another step before you actually set up the integration is to identify the top function. All right, so let's see how we might do that in this case. Now, we can tell just by, again, we have the graph, so we can quickly tell that the line is our top function. So the top of our region here is the line, and then the bottom part of our region here is given by the parabola. So we wouldn't really have to do this because we have the graph, but let's just say we didn't have the graph. How would we identify the top function? Well, you can think of it as we're looking at this section of the x-axis going from -1 to +1. So we're going from our one intersection point to our other intersection point. And we want to identify which of these formulas is giving us larger values inside this interval. And so a way to do this, we know at these endpoints, that's where the two curves have the same value. So we just want to pick a test number that sits inside here. So maybe like t equals 0 would be a good test number. And we're just going to plug this into both functions and see which one gives us the larger value. So let's try that. Let's take the test number t equals 0, and let's plug it into our parabola equation. So we get y is equal to 0 squared plus 2 times 0 plus 3. And that simplifies down to just 3. And again, let's take that same test number, but plug it into the other equation. So y is equal to 2 times 0 plus 4, which is 4. And so the way we can use this to identify the top function is whichever function gives us the larger value, well, that's the top function. So in this case, the larger value is 4. So what this is telling us basically is what we kind of could tell from the graph, but it's telling us that y equals 2x plus 4 it's the top one. So again, this is not something you would necessarily need to show if you have the graph and you can just visually see, well, there's our line, so I know that that's higher up on the page, so that's going to be my top function. But if you didn't have the graph, you could do it this way. So once we've identified the top function, now we're ready to set up our integral. So that's kind of the last part of this. Get the integral. And so we're going from intersection point to intersection point. So we're going from -1 to 1. And when we set this up, if we remember, the way we calculate the area is the top function is what we use first, and then we subtract off the bottom function. So when we do this, it's the top function minus the bottom function. All right, so what our top function was the 2x plus 4. So we're going to fill that in first. And then our bottom function, well, that was the parabola. So that was x squared plus 2x plus 3. So we get our definite integral all set up. And once it's set up like this, we could just jump right to the integration, but usually you want to try and simplify and combine like terms. So in this case, we've got a 2x here, we've got a 2x here, and we're subtracting. So those are going to cancel off. Then we've got a 4 minus a 3, so that's going to become plus 1. And then if we distribute the negative, it'll just be negative x squared. So simplifying this, this becomes the integral from -1 to +1 of 4 minus 3, which is 1. And then distribute the negative, we get negative x squared. And notice that this function here that we're going to be integrating, you can kind of see remnants of it in our work for getting the intersection points. So this function here that we're going to be integrating, you might see kind of pieces of it. It might look familiar from that work before. All right, so now we just get the antiderivative, and this just becomes an integration problem. So antiderivative of that first term is just x. Antiderivative of that second term, if we use our power rule, is 1/3 x cubed. We found our antiderivative, so now we get rid of the integral sign and the dx, and we use our vertical evaluate line, and then now we're ready to evaluate. So again, get a nice set of parentheses all set up, and when we evaluate, top number gets plugged in first, and then bottom number gets plugged in second. So you can kind of remember the way you set up the area calculation is very similar to how you actually set up and do the evaluation for a definite integral. So top number goes in first, plug it in, and we get 1 minus 1/3 times 1 cubed. and then take the bottom number, again, plug it in. We get -1 minus 1/3 times -1 cubed. And you don't have to simplify, but because these are all powers of 1 and -1, it's probably easy to maybe even simplify in your head. So that first thing would simplify to just 1 minus 1/3. And the second piece here would simplify to -1 plus 1/3. Again, because this is, we have -1 cubed, this just simplifies to -1, and then double negative becomes positive. And if we go a little bit further, this simplifies to 2 minus 2/3. And that's a positive value. Okay, so that'll do it for today. So in class, we'll be looking at a few more area calculations, and we'll see, we'll probably try another example where we go from intersection point to intersection point. And we'll also see what happens if there's only like one intersection point inside our region. So we'll see you then. Bye.